Hello everybody. So now we are going to solve this problem, which is a combination of different things regarding the change in enthalpy. So in this example, we have 100 gram moles per hour of liquid hexane at 25 degrees Celsius and 7 bars. This is the feed that we have, the original material that we have. It's liquid and it is vaporized and heated to 300 degrees Celsius. This sentence means that it's vaporized means that it's turned into vapor. Heated, it means it's being superheated to 300 degrees Celsius at constant pressure. Neglecting the effect of pressure on enthalpy, estimate the rate at which heat must be supplied. So we need to know how much heat is required to turn this liquid at 25 degrees Celsius and 7 bars into vapor, superheated vapor at 300 Celsius and 7 bars. So again, let's start with the first things first, the energy balance equation. It's just heating, so we have no work. We will ignore the effect of or the change in kinetic and potential energy. So the equation reduces to Q equals N multiplied by delta H hat. Now we want to calculate this delta H. To calculate this delta H, we need to kind of visualize what we have. So we have liquid, which is state number 1, liquid at 25 Celsius and 7 bars, and we want to convert this into vapor at 300 Celsius and 7 bars. So this liquid is a subcooled or superheated. We can know this by checking the melting point of the, or I mean the boiling point of n-hexane. Let's open the textbook and see what are the properties of n-hexane. So this is table B1. The elements here, or the materials here, or the compounds here are sorted by the name, I mean alphabetically. So if you're looking for hexane, we need to look for letter H. So this is n-hexane, and these are the information that we know. So which column we are interested in? We are interested in the boiling point. So this is 1, 2, 3, 4, the fifth number. So the fifth number, 1, 2, 3, 4, 5. So this is the boiling point of hexane. This is the normal boiling point of hexane, which means that hexane boils at 68.74 degrees Celsius under the pressure of 1 atmosphere. But the pressure here is 7 bar, which is higher than the pressure of 1 atmosphere. So it's expected to boil at higher temperature than 68. So at 25 degrees Celsius, it's definitely subcooled liquid. So to turn from liquid into subcooled liquid into superheated steam, superheated vapor, we need to go through different steps. So first it will turn into liquid at the boiling point or the boiling temperature and 7 bar, and then it will turn into vapor at boiling temperatures and 7 bar, and then it will turn into the vapor at 300 Celsius and 7 bar. The delta H here is due to the change in temperature. The phase is the same, the pressure is the same, so it is the integral of Cp dt from 25 to the boiling temperature. Now we have the second step is the latent heat of vaporization. We have only phase change, and finally we have the integral of Cp dt from the boiling temperature to 300 degrees Celsius, from the boiling temperature to 300 degrees Celsius. So this is the hypothetical path that we'll assume. So this is something that we said in the beginning of this chapter, that we assume hypothetical path because we need to calculate the change in enthalpy, and we have to stick to our capabilities. We cannot combine all of them using one equation. We have to break it into different steps. Now comes the question, are we able to calculate these three delta H hats, or we are not able? So to answer this question, we need to look for the missing parts here. The constants of Cp are going to be available in the table B2, so we can find them for liquid and for vapor phase. The boiling temperature is not known. We don't know what is the boiling temperature. We can calculate it. It's gonna take some time, but we can calculate the boiling temperature. And we can go for Antoine equation and then calculate the saturation pressure as a function of temperature, and we will see what is the temperature if the saturation pressure is 7 bars using Antoine equation. This is something we can calculate. So this is the first thing. The second thing, which is the most important thing, is do we know the latent heat of vaporization at the boiling temperature at 7 bars or not? To answer this question, we need again to revisit what we said before, that this latent heat of vaporization is the heat of vaporization at boiling temperature and 1 atmosphere. So this is not something that we know. So this is going to be the bottleneck, which will make us adjust the whole hypothetical path accordingly. So the only latent heat that we have, that we know, is for the latent heat of vaporization at 1 atmosphere and the saturation temperature, which is 68.74. This is the only latent heat of vaporization that we know. So we have to adjust the hypothetical path accordingly. Again, we said the boiling temperature can be calculated, but the latent heat of vaporization cannot be calculated at different pressures or at different temperatures. So what we can do is we will adjust the hypothetical path or update the hypothetical path. Again, we have the same starting point, the same state, and the same final state. The difference is that we will combine here two changes, change in temperature and change in pressure. And this is something that we mentioned before, that you can consider the case where you have a change in pressure and temperature. And now we will have this phase change, and then we will have again a combined pressure and temperature change. If you like, you can break this step into two different steps. One step is a change in pressure, and the second is a change in temperature. The same here, you can break this into change in pressure, then change in temperature. And this is what we did before. So you can go back to the slides that we covered before for the change in the effect of temperature change on the change in enthalpy, and see that we covered part or a case where we have change in pressure and change in temperature. So this is what we are going to do here. So now this is going to be the combined changes. This is the change in temperature from 25 to 68.74 for the liquid state, and this is the enthalpy change due to the change in pressure, which is V hat delta P. We said the enthalpy change or the enthalpy doesn't change if the pressure changes, except for liquids and solids. So this is a liquid phase, so the change in enthalpy is going to be V hat delta P, and the change in temperature is the integral of Cp dt. This is the latent heat of vaporization, which is available in the textbook, and this is going to be the same integral, which is the integral of Cp dt from 68.74 to 300. We don't have any effect of pressure, so the second term that corresponds to this is going to be 0. So finally, we can put the whole equation together. It's going to be delta H from here to there is delta H1 plus 2 plus 3, which is V hat delta P plus the integral, plus the latent heat of vaporization, plus the integral of the gas phase. So this is the whole idea of the problem. If you can get this idea clearly, then everything is going to be just calculations. I don't say it's going to be very quick, but it's going to be very systematic. So the coming is going to be just picking numbers from the text, from the tables, substituting, and calculations. There might be some unit conversions, but other than this, this is the whole idea of the whole problem. So if you can get this right, everything is going to be straightforward later. So now, if you want to calculate the change in enthalpy, this is the equation that we said. V hat delta P, of course, we know V hat is 1 over density, so it's 1 over specific gravity multiplied by the reference density. And what we're going to do is get each one of these delta H's calculated. So for the first delta H, it's delta P over specific gravity. Delta P is P2 minus P1. So P2 is 1 atmosphere, which is 1.013 times 10 power 5 Pascal. So the P1 is 7 bars, which is 7 times 10 power 5. So this is delta P. And this is the specific gravity, which we got from here, which is 86.17. I'm sorry, it's 0.659. I'm sorry, this is 80.659. And this is 1000, which is kilogram per meter cube. So if you check the units, this is going to be Pascal meter cube over kilogram. And we know Pascal meter cube is joule. So this is joules per kilogram. Remember that the units of all of the rest of the terms, whether it's latent heat, whether it's the integral of Cp dt, is kilojoules per mole. So this kilojoule per kilogram needs to be converted into joules per kilojoules per mole. So this kilogram is converted into gram, and then from gram to gram mole. Now we have the molecular weight, so we don't need to calculate anything. So just pick the number from the table. So now it's from kilogram to gram, from gram to mole. So we adjusted the denominator. For the numerator, it is joule into kilojoule. So we divide by 1000. So this is the V hat delta P term. And now this is the integral of Cp dt, and luckily for the liquid, it's only one constant. The empty slots means that they are zeros. So you have 216.3 times 10 to the minus 3, of course, dt from 25 to 68.74, which is going to be a very straightforward integration, which will be 9.38. Before we move to the next one, there is one very important an observation that we will find here, that the effect of temperature change, which is 43, it's less than 44 degrees Celsius, the delta T 44 degrees Celsius, is much more significant than the effect of almost 6 atmospheres, which is 0.078. And you compare this number to this number, how much this number represents compared to this. If I totally ignore this, it's going to be almost the same. So again, this confirms that the effect of pressure is very negligible. So we did this because we need to make sure that the numbers are accurate as much as possible. But from a conceptual point of view, this is important. But again, this is one thing that you need to keep in mind, that the effect of pressure is very negligible. For the second delta H, it's the latent heat. It's already there, which is 28.85 kilojoules per mole. Now the units are homogeneous, so you can add and subtract. It's fine. We have no problem. The final is the integral of Cp dt. Now for the gas phase, we have 4 terms, so we have to include all of them. And after the integration and substitution, it's 47.2. I'm not saying this is quick calculations. It's very systematic. So if you know how to do these calculations, things would be very straightforward. Finally, what we need to do is to add the 3 terms together, calculate the sum, and don't forget, again, this is something that's very common, that you forget why you are doing all of this. We are doing all of this because, we need to put a number here. This is all what we need to do. We know n dot, of course, it's already given, which is 100 gram moles per hour, so we need to substitute with the value of delta H. So now after we are done with the value of delta H, we can substitute in the energy balance equation. We know this is 100 moles per hour. Then you calculate it in kilojoules per hour, which will be equal to 2.37 kilowatts. So this is all what we need to do. And we went through all these calculations and the hypothetical path and checking on the hypothetical path, because we need to make sure that we are able to calculate each segment in this hypothetical path. One last thing that I want to mention here regarding this problem. If we go back to the original statement of the problem, and if we change only one word, which is the type of material, if we apply the same problem to instead of hexane to water. So if you have water that's turning into steam, and we want to do the same calculations, you would notice that if it's water, the only thing that you would do is you wouldn't need to go through all these hassles, and you wouldn't go you wouldn't need to do this hypothetical path. You wouldn't need to check if the hypothetical path is right. You wouldn't need to go and pick the constants of Cp from the table, doing the integrations, adding all the segments. You wouldn't do all of this. All what you need to do is to pick the enthalpy at state 1 from the steam table, the enthalpy at state 2 from steam table. This is exactly what we used to do in chapter 7, and calculate delta H. So this is all what you would do if it's steam. And I'm saying this because I want you to appreciate the steam table. and this is a very, very important thing. Steam table is saving us a lot of time and a lot of calculations. And this is what I said in the beginning of this chapter. In chapter 7, when we did the get the data from got the data from Steam table, we didn't even care to worry about all these details. We wouldn't think if it's the same phase, it's a different phase, if we need to do any expectations of how the material converted from this phase to this phase. It's not it wasn't of our concern. Uh, so Steam table is a very, very, very valuable resource. So since we are not dealing with Steam table or with water, we don't have hexane table. So we had to go through all this hassle because we don't have hexane table. So, and I hope this point is clear. We will solve one more example, and then this is going to be the end of this chapter. Again, just to remind you, we are not going to go through this part. It's in the textbook. If you're interested, please go and check it yourself. What we're going to do next is the effect of chemical reaction, which is the topic of chapter number 9, which is the last chapter in this course. So I'll see you next time, inshallah. Goodbye.